Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. In this episode, we're going to start off by talking about the allotropes of carbon. So these four structures here, these are all made from carbon bonding with other carbon molecules. We've got graphite, diamond, fullerene, and graphene. Let's take a look at graphite first. First off, graphite is a very good conductor of electricity. It's got a delocalized electron which can move around its structure. Furthermore, if you look at these lines here, these are very weak bonds that hold graphite together. And, you might notice that graphite is used in pencils and that's because when you rub this molecule against a piece of paper, just the friction of rubbing the pencil against the paper is strong enough to break these bonds. What happens is the graphite starts to come off in these layers, in these sheets. And so those weak bonds are actually important because they allow us to write on paper and write down and jot down our thoughts. You'll notice that each carbon is bonded to 3 other carbons, and that forms a bond angle of 120 degrees. Now diamond is bonded to 4 other carbon molecules. It does not conduct electricity very well because all the electrons are bonded and are therefore not delocalized to move around freely. And since these are bonding to 4 different carbons, the bond angle here is 109.5. This is one of the strongest materials on Earth. It is used for cutting things, other strong things like glass. Nothing can scratch diamond because it is so strong, and that's because it's forming these really solid molecular structures. This is a Buckminster fullerene. It is not a giant molecular structure, and we'll talk about that more in a sec, because it has a finite number of carbons. So the finite number is 60 carbons, and it comes together in these kind of hexagon and pentagon shapes to form this kind of ball-shaped structure. Lastly, we have graphene. This is a new molecule. It was discovered pretty recently, but it's also carbon molecule bonded to 3 other carbons, but it exists as a single layer, and it does not covalently bond with another layer below it. This molecule is the thinnest molecule and also the strongest molecule that we can make. And it's important in doing things like making nanotubes and other nanoparticle technology. Now, diamond and silicon, you can see they have very similar structures, and they actually form giant covalent structures, meaning a lot of these atoms will come together to make this really large crystal structure, and it causes these structures to be incredibly stable. Now, if you look, we looked at these patterns before, these trends. We can see that carbon here and silicon are having much higher melting points than other elements around them. That's because they form these giant covalent structures. Silicon here, if you look, silicon is, to form its giant covalent structure, it is covalently bonded with oxygen, SiO2. This is quartz, a lot of the components in like glass. But note that silicon and carbon, the reason they're so high is because they form giant covalent structures. Okay, so in the past couple chapters, we've been talking about intramolecular forces of attraction, meaning the bonds that hold molecules together. Now we're going to actually talk about the intermolecular forces of attraction. Those are the bonds between the molecules, between one molecule and another molecule. So when we're talking like, let's say the covalent bonds, those are really, really strong bonds. But now we're just going to talk about the bonds in between each of the molecules. Now, when you melt a compound or when you boil a compound, the bonds that you are breaking, melting and boiling is a physical change. So you're not actually changing the chemical structure. You're not breaking any of the chemical bonds. You're just breaking these intermolecular bonds. It's very important to distinguish. When you do a chemical change and a chemical reaction actually happens, that's when you break these chemical, let's say, covalent bonds. But if you're just melting or boiling, then those are physical changes, and those are breaking the intermolecular forces of attraction. We're going to be talking about 3 types of intermolecular forces of attraction: London dispersion forces, dipole-dipole attractions, and hydrogen bonding. Note that there's this term called van der Waals forces, and that refers to both London dispersion forces and dipole-dipole interactions. And notice from this chart, this arrow here represents increasing strength. So London dispersion would be the weakest and hydrogen bonding would be the strongest. Also note that London dispersion forces occur in all molecules. If the molecule has an electron, it's going to have London dispersion forces. Now, only polar molecules only polar molecules are going to have dipole interactions, and only molecules with H's bonded to O, N, or F are going to have hydrogen bonding. So let's talk about London dispersion forces. So normally, let's take a look at this chlorine-chlorine bond. Normally, there is no dipole, meaning this is a non-polar molecule, meaning the electrons are distributed evenly throughout the molecule. However, remember we cannot directly determine the position of an electron, and instead we can do probability. Now, since it is a probability, sometimes because of that probability, the electrons might end up on one side of the molecule instead of the other. It's just so happened that by random chance, all of the electrons happen to end up here on this side of the chlorine molecule. And because of that, there is an attraction between the negative and a positive of a neighboring atom. Since this part's becoming more negative, it's actually going to push the electrons in this molecule towards this side, making this side positive, and therefore we have this very weak attraction. Again, this happens to all molecules because all molecules have electrons. Now, it turns out that this phenomenon happens more the more electrons you have. So the larger the molecule, the more the electrons, and you actually get more of a London dispersion force. And we see this with our halogens. So with our halogens going down, we know that the weight increases and going down the table, and that means there's more and more electrons. And since there are more and more electrons, there are more chances of getting this kind of induced dipole, this London dispersion force. And that actually is going to increase the boiling point, because remember, to boil a molecule, we have to break that bond in between these two chlorine molecules. The second one is a permanent dipole or a dipole-dipole force. That is just when, so the HCl molecule, the hydrogen chlorine, is a polar molecule, meaning this part's going to be negative and this part's going to be positive because chlorine is more electronegative. It is keeping the electrons close to it. And therefore, the negative part of that chlorine is going to be attracted to the positive part of the hydrogen in another HCl molecule. And this is a permanent dipole, whereas this was a temporary dipole caused by the random moving of electrons. Now remember that this molecule, all molecules experience London dispersion forces. So in this molecule, I would say that there are dipole-dipole forces as well as London dispersion forces. If I were asked what type of intermolecular forces of attraction existed between these two molecules. Lastly, hydrogen bonding. This is whenever oxygen, fluorine, or nitrogen, NOF, oxygen, fluorine, or nitrogen are bonded with another hydrogen, you will get hydrogen bonding. And then these are really electronegative elements, oxygen, fluorine, and nitrogen, and so they are constantly pulling electrons toward them. And so we get this hydrogen bond. When you guys did the lab with the pennies, the reason the water was able to stay on there for so long was because of hydrogen bonding, kind of making those water molecules stick together. Again, this is the strongest bond out of these three that we talked about. However, remember that these bonds that we're talking about are relatively weak compared to the actual covalent bonds that we discussed before. I'm saying that the hydrogen bond is strong compared to the dipole-dipole or the London dispersion, but it is weak in comparison to the covalent bonds that we were talking about last week. So we can see here from this graph that all these molecules are very similar in their bonding. However, because of being hydrogen bonding, because of the oxygen, fluorine, or nitrogen, we get hydrogen bonding, which makes the boiling point of these molecules so much higher. And so let's just go over all of the types of bondings that we've been talking about and put them into perspective. So London dispersion forces, this is the lowest melting point, and this happens in non-polar molecules. Dipole-dipole, this is higher than London dispersion, and it is slightly miscible, meaning slightly soluble. Now, if you think of like soapy water, the reason we use soap to wash things like our clothes and our dishes and stuff is because is because soap has non-polar portions to it, so it can dissolve the non-polar stuff. And it also has polar portions to it, so it can dissolve the polar stuff. So soap and detergent and all that are really good at dissolving things because they have both non-polar and polar components to them. And you know that like dissolves like, so non-polar things will only dissolve in non-polar things, and polar things will only dissolve in other polar things. Same thing with hydrogen bonding as dipole-dipole. Since these are charged, they are miscible or will dissolve with other polar substances. Ionic bonds, remember that these conduct electricity only when they are dissolved in water, but these ionic bonds are stronger than all of these three bonds. Metallic bonds conduct electricity. They are not soluble in water, and the melting point is regulated by the valence electrons, the size, and the amount of packing of these electrons. We'll talk about those more later. And remember, giant covalent, we showed that in the graph, are the highest melting points. They are insoluble in both polar and nonpolar substance, and they don't conduct electricity except for graphite and also graphene. Okay, so let's talk about some examples and figure out which one would have the higher melting point. So when we're comparing HF and HCl, what type of intermolecular forces of attraction do we have here? Well, they both have London dispersion because they both have electrons. They're both going to have dipole moments because they're both polar, so dipole-dipoles. And this one is going to have a higher boiling and melting point because of hydrogen bonding here. Okay, H2O and H2S. We're going to have London dispersion. We are going to have dipole-dipole because they are both polar molecules. And this one's going to be higher because this one has hydrogen bonding. NH3 and PH3, again, London dispersion forces for all molecules. They're also going to have dipole-dipole interactions because when you draw these out, these are going to end up to be polar. And NH3 is the higher melting point because of, again, hydrogen bonding. Now, CH3OCH3 and CH3CH2OH. This has symmetry, so it's going to have London dispersion, but it's not going to have dipole-dipole. It's just going to have London dispersion forces. This, if you draw it out, will not have symmetry, so it will actually be London dispersion, dipole-dipole, and the oxygen bonded to the hydrogen, so we'll have hydrogen bonding there. Okay. This, remember, carbon and hydrogens are non-polar if it's just carbon and hydrogens by themselves. So this is non-polar, so the only intermolecular forces are going to be London dispersion. This one, since it has an O and an H, when you draw this out, it will actually look like this, where the carbon is double bonded to the oxygen. So we are going to have London dispersion. We are going to have dipole-dipole interactions, but we are not going to have hydrogen bonding because the oxygen has to be bonded to the hydrogen for hydrogen bonding. So this one, no hydrogen bonding, but we do have London dispersion and dipole-dipole interactions. And this last one here got kind of cut off, but we're going to have London dispersion, dipole-dipole because it's polar, and we're also going to have hydrogen bonding because this oxygen is bonded to that hydrogen. Okay, and then here's just a quick little chart that summarizes kind of the things we've been talking about. And you can look at this. You can look at this, know that ionic compounds are insoluble. They're non-soluble in polar solvents. This is talking about polar solvents. They conduct electricity. We've got giant covalent, which are non-conductors except for graphite and graphene. And the Buckminster fullerene is a semiconductor. Non-polar compounds are non-conductors, and polar compounds are non-conductors. Okay, metallic bonds. So this is a metallic bond right here. It's composed of positive ions with a delocalized electrons, meaning these electrons are free to float around. Notice that a general trend is that when we move to the right with our metals, they are going to increase in melting point, and when we go down the table, they're going to decrease in melting point. And this chart does a good job of summarizing some of the properties of metals, meaning they are good conductors of electricity and heat, they are malleable and ductile, and they have high melting points, and they are shiny and lustrous.